Tonight, we're going to look at a number that quietly rewrote almost everything we thought we knew about the universe. The sky looks crowded. Stars everywhere. Galaxies stacked behind galaxies. Light in every direction you point a telescope. Measure it properly, though, and the picture falls apart completely. Ordinary matter is almost nothing. Most of what holds anything together can't be seen at all. The space between galaxies keeps stretching, and the rate keeps changing. New measurements taken just last year suggest it isn't behaving the way anyone expected. By the end of tonight, you'll understand what's actually filling that emptiness. Why galaxies hold together when they shouldn't be able to, and why a discovery announced in the last 2 years has cosmologists reconsidering an ending they thought was already settled. Before we go further, if wondering about the sky is something you truly enjoy, tap the like button or subscribe to the channel. It costs you nothing, and it helps this channel find more people who wonder about the same things. Let's begin. The night sky looks full, stars scattered from horizon to horizon. Points of light, close together, endless. It feels like abundance. It feels like everything is there. But feeling and fact are different things. Your eyes are good instruments, but they are limited ones. They only catch light. And light, it turns out, is not where most of the universe lives. Somewhere far above you, the universe keeps its own ledger. A quiet accounting of everything that exists. And when that ledger is opened, the numbers are strange. Stars are made of ordinary matter. So are planets. So is the gas drifting between galaxies. So is every rock, every ocean, every breath you take tonight. All of it belongs to the same family of matter. The kind that shines, or reflects light, or blocks it. The kind astronomers can actually see. Chemists have a name for this family. They call it baryonic matter. Protons, neutrons, the ordinary building blocks of atoms. Everything you have ever touched is built from it. For a long time, that seemed like the whole story. Look at a galaxy, count its stars, and you have its mass. Simple, except it never quite added up. When scientists tally all the ordinary matter in the universe, something is missing. Stars, planets, gas, dust, black holes. Add every visible thing together. The total is small. Startlingly small. Ordinary matter makes up only a sliver of everything that exists, a narrow band in a much wider spectrum. The rest is there, but it gives off no light. It does not block starlight. It does not do anything that light can reveal. Astronomers call the largest hidden piece dark matter. Not dark because it is black or empty. Dark because it emits nothing at all. It does not burn. It does not reflect. It passes through ordinary matter as if it were not even there. Trillions of these particles may be passing through you right now. Silently, painlessly, leaving no trace behind. It simply is. And by every measurement, there is far more of it than there is of us. Of the stars, the planets, the galaxies we recognize. Dark matter outweighs ordinary matter by a wide margin. Not slightly more. Several times more. Then there is a second unseen presence, something even larger and even stranger. Astronomers call it dark energy. It is not made of particles in the way matter is. It behaves more like a property of space itself. A quiet pressure, spread through everything, everywhere. You cannot point a telescope at it directly. You can only see what it does to everything around it. Together, dark matter and dark energy make up the overwhelming majority of the universe. Ordinary matter, the stuff of stars and skin and stone, is a footnote, a small, glowing exception in a mostly invisible whole. This is not a guess. It is not a single observation that could be wrong. It comes from several completely different methods. Methods that do not depend on each other. And they all point to the same answer. The first clue came from galaxies themselves. From watching how fast they spin. Stars near the edge of a galaxy should move slower than stars near the center. That is how gravity is supposed to work. The outer stars feel less pull, so they drift more gently. It is the same reason outer planets orbit the sun more slowly than inner ones. Astronomers expected galaxies to behave the same way. But when astronomers measured real galaxies, the outer stars were not slower. They moved almost as fast as the ones near the core. Far faster than the visible matter could explain. Something unseen had to be holding those outer stars in place. Something with enough mass to keep them from flying off into space. Something spread out far past the edge of the visible disk. Not stars. Not gas. Something invisible, wrapped around the galaxy like a silent shell. The math only worked if that invisible mass outweighed the visible stars by a wide margin. Galaxy after galaxy told the same story. Spirals near and far, all spinning too fast for their own visible weight. The second clue came from light itself, not starlight this time, but the path it takes. Massive objects bend space around them. And light, traveling through that space, bends along with it. A distant galaxy can act like a lens. Its gravity warps the light passing near it, smearing the image of anything further behind it, sometimes stretching a single galaxy into a faint arc of light. Astronomers can measure that smear. They can calculate exactly how much mass it would take to bend light that much. And again, the answer comes back larger than the visible matter allows. Far larger. The bending only matches reality if invisible mass is doing most of the work. Two completely different techniques. One watching motion, one watching light. Built by different scientists decades apart. Neither depends on the other, and they arrive at the same hidden mass, hiding in the same places. The third clue is older than either of those methods. It comes from the faint afterglow left behind by the early universe. A dim, ancient light that still reaches us from every direction. Almost perfectly smooth, but not quite. Tiny variations are baked into it. Subtle patterns, frozen in place since the universe was very young. Those patterns carry information. Information about what the early universe was made of. How much ordinary matter it held. How much unseen matter shaped its structure. How space itself was already beginning to stretch. This afterglow was released long before any star ever formed. Long before any galaxy had taken shape. It is the oldest light there is, a record from the universe's infancy. When scientists read those patterns carefully, the proportions match. The same small share for ordinary matter. The same dominant share for the unseen. Three methods. Spinning galaxies. Bent starlight. Ancient afterglow. None of them built on the others. None of them assuming the answer in advance. And still, they agree. That agreement is what makes the picture hard to dismiss. If only one method pointed to invisible mass, it could be an error. A flaw in the instrument, a mistake in the math. A single telescope pointed the wrong way. But three unrelated approaches, converging on the same fraction, is different. It suggests something real. Something woven into the fabric of the universe, whether we can see it or not. So when you look up tonight, remember what you are actually seeing. Every star, every faint smear of galaxy, every planet in this solar system. All of it drawn from the same small slice of existence. A slice that adds up to only a modest fraction of everything there is. Everything you have ever loved fits inside that slice. The rest surrounds it, unseen, unmeasured, except by what it does. It holds galaxies together. It bends the light that passes near it. It leaves its fingerprint on the oldest light in the sky. You are made of the rare part, the visible part, the part that gathers into stars and planets and skin. Most of the universe took a different path entirely. It never needed to gather into anything you could name. It simply anchors everything else, patiently, from somewhere just out of reach. And the sky above you, full as it looks, is mostly built from something your eyes were never made to catch. Something steady, something enormous and calm, and content to stay unnamed. Something that has been there since the very beginning, holding its place without asking to be found. The stars are the exception. The rest is the foundation. And the universe has always rested on that foundation, whether we noticed or not. Deep in the disk of a spiral galaxy, stars trace wide, patient circles. They move at speeds that should tear the galaxy apart. Out at the edges, far from the crowded center, stars orbit almost as fast as stars near the core. That should not happen. At least, not if gravity from the visible stars and gas is all that's holding the galaxy together. Gravity from ordinary matter falls off with distance. Stars farther out should slow down. The way planets slow down the farther they sit from the sun. Mercury races. Neptune drifts. Most of the sun's mass sits at the center, so the pull weakens with distance in a predictable way. That pattern holds for a solar system. It breaks down completely across a galaxy. A galaxy is not a solar system. Its mass is not concentrated in one bright point at the middle. Astronomers measured this by studying the rotation of nearby spiral galaxies. They tracked how fast stars move at different distances from galactic centers. Each measurement added another point to a growing chart. The results were consistent, chart after chart. The results were strange. Stars at the outer edges kept pace with stars much closer in. Stars far from the crowded center simply refused to slow down. The rotation curve, plotted on a graph, should slope downward. A galaxy with most of its mass concentrated near the core would show exactly that slope. Instead, it went flat. Flat almost all the way to the visible edge of the galaxy. Astronomers checked the numbers again. The pattern held. Galaxy after galaxy. Only one thing explains a flat rotation curve. There has to be more mass present than anyone can see. Mass that isn't concentrated where the light is. Mass that extends far beyond the visible disk, out into the dark. Mass that no photograph has ever captured. Picture the stars near the edge of a galaxy as if they sat on a giant carousel. If only the visible matter were pulling on them, they would drift outward, spinning loose from the center. Instead, something unseen keeps them locked in place, moving fast without ever flying away. That something has to be everywhere the stars are, not just clustered in the bright middle. A galaxy, seen this way, is more than its glowing spiral arms. Around it sits an enormous invisible sphere, stretching out in every direction, far past where the last visible star sits. A halo, astronomers call it. Much bigger than the disk of stars sitting inside it. Much heavier, too. The stars you can see form only the bright core of something much larger. Stars, gas, and dust, everything you can photograph, make up only a small fraction of the whole. The rest gives off no light. None at all. It does not glow. It does not absorb starlight or scatter it. It does not interact with a camera, a telescope, or a photographic plate. Every wavelength of light passes through it as if it weren't there. It only pulls. Its gravity holds fast-moving stars in their orbits. Without it, those stars would simply fly outward. The galaxy would unravel, its spiral shape dissolving into scattered debris. Instead, galaxies persist for billions of years. Something invisible is doing the holding, quietly, across the entire disk. Scientists call this substance dark matter. The name describes what it lacks, not what it is. Dark, because it emits no light of its own. Matter, because it has mass. And mass bends space the way any mass does. It doesn't glow, and it doesn't shine, but it still weighs something. For decades, the rotation curves stood as the clearest evidence that dark matter exists. But rotation curves only tell you about speed. They tell you an object is missing. They do not show you where that object sits. They trace an outline without ever filling it in. For that, astronomers needed a different kind of evidence. They needed to see the effect of mass directly, written across the sky itself. Massive objects bend the space around them. Not just stars and planets. Anything with mass does this. Even mass no telescope can see. Mass does not just sit in space. It curves it. Light traveling near a massive object follows that curve. A straight path becomes a gentle bend. From Earth, that bend looks like a distortion, a warping of the image behind it. Astronomers call this gravitational lensing. A galaxy cluster, sitting between Earth and some brighter, more distant galaxy, acts like an enormous magnifying lens. The cluster's gravity does the bending, not a piece of glass. Light from the distant galaxy passes near the cluster and bends around it. The image of the distant galaxy on the other side stretches. It smears into an arc. Sometimes it splits into multiple copies, spread across the field of view like reflections in a curved mirror. Each arc, each smear, each doubled image carries information. The amount of stretching depends on one thing. Mass. More mass bends light more sharply. Less mass bends it more gently. By measuring exactly how much the light bends and in what pattern, astronomers can calculate the total mass doing the bending. Not just the mass of the visible galaxies inside a cluster. All of it. Every last invisible bit. Every particle that never once gave off a photon of its own. This method does not require detecting a single photon from the dark matter itself. It only requires watching how light moves around it. No camera has to catch the dark matter directly. Gravity leaves a trace, whether or not anything glows. When astronomers apply this technique to galaxy clusters, the results echo what the rotation curves already suggested. The visible galaxies, all their stars and gas and dust combined, account for only a small share of the total mass. The rest bends light from somewhere else, somewhere with no matching glow. Using lensing data, scientists have built detailed maps. Maps that plot where mass sits within a cluster, point by point, without ever photographing the mass directly. These maps often show something remarkable, something no photograph of the cluster alone could reveal. The densest concentrations of inferred mass do not always line up neatly with the brightest galaxies. Light and mass, it turns out, don't always sit in the same place. Sometimes the mass extends into regions that look, through an ordinary telescope, almost completely empty, extended, diffuse, and utterly dark. Yet gravity is there, bending starlight, leaving its signature in every distorted arc. Gravitational lensing turns invisible mass into something almost like an outline, not a photograph. A shadow, cast by pull instead of light. A map drawn entirely from the way space itself has been bent. Astronomers sometimes describe the technique as weighing a cluster without ever seeing what's on the scale. The scale itself is the sky. The needle is the curve of starlight passing through space that isn't quite empty. Every arc of bent light is a reading on that scale. Combine this with the rotation curves of individual galaxies, and a consistent picture emerges. Two completely different methods. Two completely different ways of looking at the sky. Galaxies sit inside vast halos of unseen material. That material outweighs the visible stars by a wide margin. Rotation curves trace its pull from the inside, one orbit at a time. Lensing maps trace its shape from the outside, one bent arc at a time. Together they point to the same hidden scaffolding. And yet no instrument has ever captured a direct image of it. No detector on Earth has confirmed exactly what it's made of. Only its effects are visible. Its presence, not its substance. A galaxy spinning faster than it should. Starlight arcing where there is nothing bright enough to explain the bend. Two separate kinds of evidence, gathered through entirely different methods. Both point toward the same conclusion. Most of the mass out there gives off nothing to see. Close your eyes and picture that hidden sphere, wrapped around every galaxy you have ever looked up at. It has been there through every night sky you have ever watched. Unlit, unmeasured except by the pull it leaves behind. Far away, two clusters of galaxies met. They did not meet gently. Each cluster carried thousands of galaxies. Each galaxy carried stars, dust, and gas. Between the galaxies, something larger waited. Vast clouds of hot gas. Gas hotter than the core of any star. This gas glows in X-rays. It is invisible to human eyes. But telescopes built for X-rays can see it. And this gas holds most of the ordinary matter in a cluster. More than the stars, more than the galaxies themselves. When the two clusters collided, their stars mostly passed through. Galaxies are mostly empty space. Stars rarely touch other stars. So the galaxies slid past each other, barely slowed, still carrying their shape, still carrying their motion. But the gas clouds did not slide through so easily. Gas is not empty space. Gas is made of particles, packed close together. When the two gas clouds met, they collided directly. Friction took hold. The collision dragged the gas backward. It slowed the gas down. It stripped the gas away from the galaxies that once carried it. The galaxies kept moving. The gas fell behind. Two clusters became four separate clumps. Galaxies on one side, gas on the other. Astronomers named this collision the bullet cluster. The name comes from the shape of the hot gas. It trails behind the galaxies like a bullet's shockwave. A visible record of the impact, frozen in light, still arriving after a long journey across space. Even the brightness of the gas told a story. The hottest, densest gas sat at the leading edge, compressed by the impact. Cooler gas trailed farther back, stretched thin behind it. Every layer marked a different moment of the same collision. This alone would be an interesting picture. Two ordinary things, pulled apart by physics. But there was a second measurement to take. Astronomers did not only look at where the light was, they looked at where the mass was. Mass bends space. This bending is called gravitational lensing. Light from galaxies far behind the cluster passes through this bent space. The light gets distorted, stretched, smeared into faint arcs. By measuring these arcs, astronomers can map where the mass actually sits. Not where the light is, where the gravity is. This method does not care what the mass is made of. It only responds to how much mass is there and where. So the astronomers built a map of gravity across the whole collision. Then they compared it to the map of the glowing gas. If ordinary matter held most of the mass, the two maps should align. The gravity should sit where the gas sits. That is where nearly all the ordinary matter was found to be. The maps did not align. The gravity was not centered on the gas. It was centered on the galaxies. Two clumps of mass, sitting where the stars were, not where the gas was. The gas had been slowed and left behind. But the gravity had not slowed at all. It had passed through, unaffected, exactly like the galaxies. Something was carrying most of the mass through the collision. Something that did not interact with the gas and did not glow. Something that felt no friction at all and left no trace in any telescope. This is the significance of the bullet cluster. It separates two things that are usually tangled together: the location of ordinary matter and the location of gravity. In most systems, these overlap. You cannot easily tell which one is doing the pulling. The bullet cluster pulled them apart, physically, in space. And when they were pulled apart, gravity did not follow the gas. It followed something else, something unseen, passing through the whole collision like it wasn't there. Whatever it is, it does not collide, and it does not slow down. It does not glow in X-rays or any other kind of light. It only pulls, silently, from a distance. Astronomers call it dark matter, not because they know what it is made of, but because it casts no light of its own. The bullet cluster is often called direct proof of dark matter's existence. Not just a hint from equations, not just numbers that fail to add up. A physical picture. Two kinds of matter, torn apart by a collision, showing themselves separately. The ordinary matter, glowing and slowed. The unseen matter, dark and unslowed, sitting in a different place for anyone to map. Since the bullet cluster, astronomers have found more like it. Other cluster collisions, with the same pattern repeating. Gas lagging behind, gravity moving ahead, wrapped around the galaxies. The pattern holds each time it is tested. It does not depend on one lucky observation. It depends on physics that repeats. Whatever this unseen mass is, it fills the space between galaxies. It fills the space between clusters. It outweighs the ordinary matter, cluster after cluster. You are made of ordinary matter. Every star you have ever seen is made of ordinary matter. Every planet, every comet, every grain of dust, all of it is a minority. A small fraction of what actually holds the universe together. The rest moves through collisions like a ghost, unbothered by impact, unbothered by friction, only visible through its pull on everything else. The gas remembers the collision in its slowed, dragged shape. The galaxies remember it in their undisturbed paths. And the gravity remembers it too, sitting apart from both. Three separate records of the same single event, written in light, in motion, and in the bending of space. None of them agree on where the mass should be, unless most of the mass was never ordinary at all. The bullet cluster sits quietly in its patch of sky. Two shapes of gravity, drifting apart from two shapes of light. A slow-motion collision already finished, its evidence still arriving. Photon by photon, crossing a distance too vast to picture. Proof that the universe holds more than what can be seen. More than what can be touched or measured directly. A universe built mostly from something that leaves no light behind. A shape without a source, a pull without a body. A map that does not match the picture you would expect. Astronomers have studied this collision for years since it was first mapped. Every new observation has confirmed the same separation. The gas stays behind. The mass moves on. No ordinary explanation has managed to close that gap. Some have tried modifying the laws of gravity instead, changing the rules rather than adding unseen matter. But those attempts struggle here, in this one collision, more than anywhere else. A modified law of gravity should still trace the visible mass. It should still follow the gas, since the gas holds most of what glows. Instead, the pull follows the galaxies, where the unseen mass gathers. That distinction is hard to explain away. It is easier to explain by adding something unseen, something that outweighs the glowing gas by a wide margin, something that's shaped where the gravity actually sits. The bullet cluster does not prove what dark matter is. It only proves that something is there. Massive, quiet, and indifferent to light. Drifting apart from the gas. Drifting apart from the stars, carrying most of the weight of 2 entire galaxy clusters. Unseen and unmoved, long after the collision ended. 2 clusters, once separate, now locked in this slow drift forever. The light from that collision is still crossing space to reach us. Every image taken adds one more layer to the same quiet proof. Matter that glows, matter that doesn't, and the gravity that ties them, not in the same place, not moving the same way. A single frozen collision, still arriving, photon by photon, across the dark between here and there. For a long time, scientists believed the universe was slowing down. That belief made sense, because gravity pulls everything together. Every galaxy pulls on every other galaxy, tugging gently across the dark. The expansion that began at the very start should have been losing steam the entire time. Slower and slower, forever, that was the expectation. 2 teams of astronomers set out to measure exactly how much it was slowing. This was the late 1990s. They needed a way to measure distance across billions of light years, so they turned to a special kind of dying star. It is called a Type 1a supernova. These explosions happen in a very specific way. A white dwarf star pulls material from a companion, growing heavier and heavier. At a precise mass, it detonates. Because the mass is always nearly the same, the explosion is always nearly the same brightness, which makes it useful in a very particular way. Astronomers call this a standard candle. If you know how bright something truly is, you can tell how far away it is. The dimmer it looks, the farther it must be. Researchers scanned the sky for these rare, brief explosions. Each one flares for a few weeks, then fades. They found dozens of them, scattered across deep space and deep time. The light from these supernovas had traveled for billions of years before it ever reached a telescope on Earth, carrying information from a much younger universe. The teams measured the brightness of each one, then compared it to the redshift of its host galaxy. Redshift tells you how fast something is moving away. Combine distance with speed, and you can trace the history of expansion. The astronomers expected to find a universe that used to expand faster, dragged down over time by the gravity of all that matter. They thought it would slow gradually, the way a thrown ball slows as it rises. The data came back strange. The distant supernovas were dimmer than expected, not brighter. Dimmer means farther away than the models predicted. Farther away than expected means the expansion had not been slowing down at all. It meant the universe was expanding faster now than it used to. The expansion was speeding up. Both teams checked their work. They looked for errors and considered dust in space that might dim the light, or contamination from other sources entirely. They reran the calculations many times, from different starting assumptions. Each time they arrived at the same place. The result held. By the end of the decade, both teams announced the same conclusion. The expansion of the universe is accelerating. This was not a small correction to an existing idea. It overturned a basic assumption about how gravity should govern the cosmos. For decades, the debate had been about how much the expansion was slowing. Now the question became why it was speeding up at all. Something had to be pushing space outward. Something strong enough to overpower the gravitational pull of every galaxy, star, and planet combined. Scientists needed a name for this unknown cause. They called it dark energy. The name does not describe what it is. It only marks what it does. Dark energy is not a form of matter. It does not clump into stars or planets. It does not shine, and it casts no shadow. It seems to be a property of space itself. The more space that exists, the more of this effect there is. As the universe expands, there is more space between galaxies, and that means there is more dark energy pushing them apart. And with more push, the expansion accelerates further. More space creates more push. More push creates more space. The cycle feeds itself, quietly, without any center and without any edge. This idea was not entirely new. Decades earlier, before any of these measurements existed, Albert Einstein had considered something similar while working through his equations of general relativity. At the time, most scientists believed the universe was static, neither expanding nor contracting, just existing, unchanging forever. But Einstein's own equations did not allow for a stable, unchanging universe. Gravity would cause it to collapse. To fix this, Einstein added a term to his equations. He called it the cosmological constant. It acted like a repulsive force, spread evenly through space, built for one purpose only. It counteracted gravity. It held the universe still, at least on paper. At the time, this was purely a mathematical patch that solved a problem in the equations. There was no observation yet showing the universe was static. There was also no observation showing it was expanding. Later, evidence emerged that the universe was expanding after all. It was not sitting still the way Einstein had assumed. Once that became clear, the reason for his added term disappeared. Einstein removed the cosmological constant from his equations. He reportedly called it his greatest blunder. The idea was set aside for most of the 20th century. It became a historical footnote, a patch that was no longer needed. Then came the supernova observations of the late 1990s. The universe was not just expanding. It was expanding at an increasing rate. Something was needed to explain that acceleration. Physicists returned to Einstein's old equations, dusting off a term that had sat unused for generations. They tried it again, in a completely different role. The cosmological constant fit remarkably well. A constant, steady push, embedded in the fabric of space, matched the data. The term Einstein once abandoned had a new purpose. It was not holding a static universe still. It was driving an expanding universe faster. The same piece of mathematics, built for one wrong idea, turned out to describe a different truth entirely. This does not mean Einstein predicted dark energy. He was solving an entirely different problem, based on a wrong assumption about a static cosmos. But the tool he built decades earlier turned out to be useful again, in a universe he never imagined. Today, the cosmological constant is one leading explanation for dark energy. In this view, empty space itself carries energy. Every cubic meter of nothing contains a tiny, constant push outward. As space grows, so does the total amount of this energy. There are other proposed explanations as well. Some involve a dynamic field that changes over time. Some involve modifications to gravity itself on the largest scales. But the simple cosmological constant remains the model that best fits decades of accumulated observation. It has been tested again and again against new data, and it has held up. Whatever its true nature, its effect is measurable. Distant galaxies are not just receding. They are receding faster than they were before. A pressure, with no known source. A force that grows as space grows. It stretches every measurable distance a little more each year. Galaxies once close enough to interact are drifting beyond reach. The space between all things is quietly widening. Not because of any explosion, not because of any collision. Simply because empty space itself carries this outward pressure. Everywhere. All at once. There is no center to push from, and it does not appear to be slowing down. Every study since has confirmed the same trend. Different methods, different instruments, different teams working independently. All arrived at the same answer. The acceleration is real. The universe found at the end of the 1990s was already stranger than anyone expected. It was not coasting toward a gentle stop. It was pressing its foot down, harder, on emptiness itself. That pressure has not eased since. Night after night, telescopes keep finding the same distant, dimmer light and the same quiet answer. The universe is not winding down. It is leaning further into the dark. A little more with every passing year. /text, /invoke. Something invisible holds the universe together. It has never been seen, never been touched, never been captured in a single photograph. Scientists gave it a name anyway. Dark matter. Alongside it sits something even stranger. Dark energy. Together, they make up most of everything that exists. And yet neither has ever revealed itself directly. For decades, their presence was known only through absence, through gaps in the math, through galaxies that spun too fast to hold themselves together, unless something unseen was holding them instead. One spacecraft was built to trace the shape of that unseen something. Its name is Euclid. Launched in 2023 by the European Space Agency, it does not chase light the way other telescopes do. It chases shadows instead. Not stars, not planets, not even galaxies themselves, not directly. Euclid was built to find the scaffolding behind them, the unseen structure that holds the visible universe together. It cannot look for that structure directly. That would be impossible. Light does not bend around nothing. So instead, Euclid watches how light bends around everything. It studies billions of galaxies scattered across the deep sky. Their light travels for millions of years before it ever reaches the mirror. Along the way, it passes through hidden mass. And it bends, ever so slightly, the same gravitational lensing traced earlier in this story. It is subtle, far too subtle for the eye. But not too subtle for Euclid's instruments. They watch for the faint distortion hiding in galaxy shapes. A slight stretch here, a slight curve there. Across billions of galaxies, the distortions begin to align. They trace the outline of something that casts no light of its own. Each galaxy, on its own, tells very little. Its shape could be anything, a little rounder or a little longer, for reasons all its own. But gathered by the billion, the shapes stop looking random. They lean the same way in certain patches of sky. They curve together, faintly, like grain running through wood. That shared lean is the signature Euclid was built to find. It can only be seen in the crowd, never in a single galaxy alone. From that crowd, something new begins to take shape. Not a photograph. A structure of filaments and voids. Threads of matter linking clusters of galaxies, with enormous stretches of emptiness between them, reaching back through both space and time. The scale is difficult to hold in the mind. Euclid observes a wide stretch of sky, mission after mission. Over its lifetime, it will image billions of galaxies, some so distant their light left them long before the Earth existed. By capturing them, it looks backward through time. It sees the universe as it once was. Layer by layer, a record of cosmic history builds. How structure grew. How galaxies clustered. How the unseen scaffolding shaped everything that came after. The mission's first full data release came in 2024. Early images revealed sweeping fields of galaxies. Spirals and ellipses scattered like sand across the frame. Each one shaped in part by something no one has ever seen. Scientists studying that first release worked slowly. They measured the tilt of galaxy after galaxy, sorting them by distance, by brightness, by the faintest distortion. Rough outlines appeared, still coarse, still full of gaps. Enough to know the method worked, not yet enough to call it finished. In 2025, deeper sky surveys followed, with wider fields and sharper detail, stretching further into the dark spaces between galaxies. Astronomers pored over the new data, searching for filaments, for the faint fingerprints of matter that emits no light at all. The gaps from the year before began to close. Regions that had looked empty showed faint threads after all. Regions that had looked dense turned out to hold less than expected. Slowly, a picture took shape. Not of stars, but of the space between them. A hidden geometry drawn out one observation at a time. It is strange to think about. A telescope pointed at the sky, searching for absence, cataloguing galaxies not for what they are, but for what bends around them. Unseen, Euclid does not claim to know what dark matter is made of. No instrument yet does. It cannot say what dark energy truly represents. That answer still waits somewhere ahead. What it offers instead is an outline, a record of where the unseen mass gathers, where it thins, where the universe stretches into near total emptiness. The data does not explain the darkness, it only traces its shape. And somehow, that is enough to feel vast, enough to feel unsettling in a quiet way. Because the outline keeps growing, field by field, galaxy by galaxy. And it keeps showing the same thing, that most of what holds the universe together cannot be seen. The visible universe, the stars, the planets, the glowing clouds of gas, all of it sits like a thin coating over something else. Something vast, something Euclid can trace but never touch. Each new image adds another piece to the pattern. A filament here, a cluster there, a stretch of nothing spanning millions of light years. The telescope keeps working. Quietly, far from Earth, collecting light that left its source long before humans existed. Somewhere in that data, patterns repeat. The same kind of structure again and again. As if the universe had drawn its own skeleton and left it there, waiting for something to notice. Euclid noticed. It has been noticing since 2023. Each survey adds another layer to the record. A wider field, a deeper exposure, another slice of sky folded into the growing atlas. Researchers compare each new release against the last, looking for shifts, looking for places where matter grows denser or thins to almost nothing. Every comparison sharpens the picture a little more. The catalogue of galaxies grows alongside it. Millions logged, then tens of millions. Each one a data point in a structure too large to see whole. Even from orbit, no single image holds the entire pattern. It has to be assembled piece by piece, survey by survey, slowly filling in a chart of things no one can see directly. A chart of shadows cast by nothing visible at all. And still the shape holds together. Still it stretches across enormous distances. Still it waits to be understood. For now, it is simply traced, outlined in light that bent long before it reached us. A quiet record of the dark, growing wider with every pass overhead. A number sat quietly inside a mountain of data. For decades, nobody questioned it. Then, one year, it began to move. Its name is DESI, the Dark Energy Spectroscopic Instrument. It holds thousands of tiny robotic fibers. Each one can point at a single galaxy. Each one can catch that galaxy's light. Each fiber moves on its own, guided by a small motor. Together, they can aim at many galaxies at once. Then the whole array shifts and aims again. Night after night, DESI turns toward the sky. It gathers light from millions of galaxies. It measures how far away each one is. It measures how fast each one is moving away from us. This is slow, patient work. It takes years to build a map this large. Galaxy by galaxy, the map grows outward. Some of the light DESI catches left its galaxy billions of years ago. By reading that light, scientists read the universe's past. But the map holds a secret. Buried inside all those galaxy positions is a number that describes dark energy. For decades, that number was assumed to be fixed, a constant, the same yesterday, today, and a billion years from now. Scientists gave it a name: the cosmological constant. It fit neatly into the equations. It explained why the universe expands faster every year. It became part of the standard model of everything. A single value plugged into the math, and the math held together. No need for it to shift with time. No need for a history behind the number. Just a fixed weight, pressing outward on the fabric of space. A weight that never seemed to change in any measurement anyone had made. Most people who study the cosmos accepted it, not because it was proven beyond doubt, but because it worked well enough. It matched decades of observations, again and again. So the constant sat quietly at the center of modern cosmology. Textbooks were built around it. Careers were built around it. Then, in March 2024, DESI released its first major results. The team had measured light from millions of galaxies and quasars. They traced the universe's expansion across billions of years. And something did not sit quite right. The data leaned away from a constant, only slightly. Not enough to be certain, but enough to notice. Enough for the team to run the numbers again, and then again, more carefully still. They checked their instruments. They checked their calibrations. The lean did not disappear under closer scrutiny. It stayed, small and steady, inside the data. The numbers suggested dark energy might not be fixed at all. It might be changing, weakening, ever so slightly, as time passes. Scientists are careful people. They do not shout when they see a small deviation. They wait. They gather more data. They check it against other measurements. So the DESI team kept working. They pointed their robotic fibers at the sky again, night after night, for another full year. By March 2025, they had 3 years of data instead of 1. Millions more galaxies, spread farther across the sky than before. A far larger, far more detailed map of the universe. And the hint from the year before did not go away. It grew stronger. The new data still pointed toward a dark energy that evolves. Not a fixed number, but a moving one. Something that may have been stronger in the ancient past, and weaker now. 3 full years of measurement made the case sharper than 1 year alone. Not proof, but a pattern that held steady the longer they looked. A pattern spread across millions of galaxies and quasars. Too many to easily explain away as noise. Statisticians checked the result against alternative explanations. Instrument error, calibration drift, mistakes in the pipeline. None of it made the pattern go away. The signal held, quietly, under every test they threw at it. This matters more than it might seem. Dark energy is not a small detail in physics. It shapes how galaxies spread apart across billions of light years. It is the reason galaxies are flying apart faster each year. It decides how the universe will end. If it is a true constant, the ending is one story: endless expansion, slow and cold, forever. But if dark energy changes, the ending could be different. Nobody knows exactly how different. The question sits at the edge of what current instruments can resolve. Answering it fully may take another decade of watching the sky, night after patient night. Scientists have started sketching out other paths. Some models suggest dark energy simply keeps fading. Slower and slower expansion, easing off over trillions of years. Others go further. They ask a stranger question. What if dark energy does not just fade? What if it flips? In a small number of theoretical models, this is possible. Dark energy would not vanish. It would reverse. Instead of pushing galaxies apart, it would begin pulling them back, an expanding universe, slowing down, then stopping, then contracting. Space itself folding inward, the way it once unfolded outward. Galaxies that once raced apart would begin drifting closer, slowly at first. Some call this a big crunch. None of this is settled physics. It is a possibility that follows if the weakening keeps going. The evidence right now only shows a hint, measured across 2 releases, 1 year apart. Nothing about DESI's data proves the universe will reverse. Nothing proves it will not. That is the strange position scientists find themselves in tonight. A number they trusted for decades no longer feels fixed, and they are not sure yet what to trust in its place. Somewhere in the DESI archive sit rows of numbers gathered across 3 years of careful watching, from 2022 onward. Spreadsheets built from starlight. Somewhere in those columns, a universe reveals a small piece of itself. Not with a flash, not with a bang, just a quiet shift in a decimal point, a drift barely there, repeated in the light of galaxies so far away their light is ancient, repeated in quasars burning at the edge of what can be measured. It is easy to miss something like that. It is easy to assume the old answer still holds. But DESI's instruments do not get tired. They do not stop checking. Each night, more robotic fibers swing toward another patch of sky. Each night, more galaxies join the map. The team plans to keep collecting data for years to come. More seasons of observation. More light gathered from more distant galaxies. Enough, eventually, to settle the question either way. Other observatories will eventually check the same numbers. Independent measurements, built on different instruments, aimed at the same distant galaxies. If they agree with DESI, the case grows harder to dismiss. If they do not, the constant may hold after all. Either way, the answer will come slowly. Built from years of patient nights, not a single discovery. Until then, the number stays uncertain. A quiet unease sits underneath a settled idea of the cosmos. Something once thought fixed now seems to be moving. Somewhere out past every galaxy DESI has already mapped, the pattern may continue. An unseen force, thinning with time. Its true shape still hidden in the dark between the stars. A question resting quietly over every galaxy in every direction. One that will not be answered tonight, or this year. Perhaps not for many years after that. For now, the telescope on Kitt Peak keeps watching, fiber by fiber, galaxy by galaxy, night after quiet night. Gathering evidence for an answer that has not yet arrived. In 2025, a new set of instruments in Chile started returning its first pictures of the sky. The images were not ordinary. Each one held more galaxies than a person could count in a lifetime. The project behind them is called the Vera C. Rubin Observatory, named for the astronomer whose measurements once revealed motion that gravity alone could not explain. The telescope carries her name into a new kind of survey. In 2025, it was the first light from an observatory built for one enormous task. Astronomers had waited years for this moment. Some had waited their whole careers. The observatory carries the name Vera Rubin. She was an astronomer who spent decades studying the edges of galaxies. Her measurements once revealed motion that gravity alone could not explain. Evidence that still anchors the case for dark matter today. She never saw the substance she helped reveal. She only saw its fingerprints, written in the motion of stars. Now her name sits on a mountaintop in the Chilean Andes. The air there is thin and dry. The sky is famously dark. Few places on Earth offer a clearer view of the stars. It is why astronomers chose this ridge for their new telescope. The observatory bearing Rubin's name looks outward every clear night. It is meant to photograph the entire visible sky, again and again. Not once. Not twice. The plan calls for 10 straight years of nightly observation. Each night it captures a wide swath of the heavens. By morning, that data has already started its journey to waiting computers. Slowly, an unprecedented record takes shape. The scale of the project is difficult to hold in the mind. Billions of galaxies will pass before its lens. Each one catalogued, measured, and placed within the growing survey. Some are enormous spirals, larger than our own. Others are faint smudges, barely brighter than the black around them. The telescope does not discriminate between them. It records what it sees. One exposure after another, night after night, without pause. Along with distant galaxies, it watches closer things too. Objects within our own solar system drift through its field of view. Asteroids move slowly against the fixed background of stars. Comets swing in from the outer dark on long, silent orbits. The observatory is built to catch them as they move. Because it scans the same regions repeatedly, it notices change. A speck that shifts position between images reveals itself as a moving object hiding in plain sight. Software sifts through the flood of new data within minutes. It flags anything that looks different from the night before. New objects turn up often, once the nightly comparisons begin. Some pass closer to Earth than expected. None pose any danger, but their existence had simply gone unnoticed until now. The telescope's design makes this kind of discovery routine. Its camera is enormous by any standard. It can capture a wide slice of sky in a single exposure. Photographing that much sky at once saves years of work. Other telescopes must aim narrowly, one small patch at a time, night after night, for a fraction of the coverage. This one drinks in whole constellations in a single glance. That width, combined with its sensitivity, is what makes the survey possible. Nothing quite like it has flown or stood on Earth before. Engineers spent decades designing the mirrors and mounts to make it real. The location itself required patience. Clear nights, high altitude, and steady air are rare in combination. Chile's mountains offered all three. Local winds are calm enough not to blur the stars. The atmosphere above is thin enough not to smear their light. Even so, no telescope escapes the atmosphere entirely. Every photon still passes through miles of shifting air before it lands. Engineers correct for this as best they can. What arrives on the sensor is close to the true shape of the sky. The first released images stunned even the scientists who built the instrument. A single frame revealed a vast field of galaxies at once. Faint spiral arms curled beside brilliant, compact clusters. Threads of light traced out, where matter had gathered over billions of years. Viewers who saw the images described a quiet kind of awe. It was not one galaxy that moved them. It was the sheer number, scattered without end across the frame. Each point of light in that image was itself a galaxy. Each galaxy held billions of stars of its own. The mind resists a truth like that. It settles into something calmer instead. A quiet acceptance that the universe is larger than any single glance can hold. Scientists describe the survey's purpose in careful, technical terms. They speak of cataloging structure, measuring distances, tracking motion across time. They aim for a precision no earlier survey has matched. But underneath the language is something simpler. They are building a record of everything visible from one dark mountain, night by night, for 10 years. A record no human eye could ever compile alone. Each new image adds to a growing archive. Over the coming decade, that archive will grow into something enormous. Researchers around the world will study it for decades to come. Discoveries buried in the data may not surface for years. Someone, someday, may find a faint signal that nobody expected. For now, the observatory keeps its steady rhythm. Sunset comes to the Chilean Andes. The mirrors open to the sky. Motors turn quietly, aiming the telescope at its next patch of stars. A shutter opens, holds and closes. Photons that traveled for millions of years land silently on a sensor. Then the telescope moves on, unhurried, to the next patch of sky. This will happen again tomorrow night. And the night after that. Each repetition adds a small piece to an unfinished record of the sky. Drawn one exposure at a time, galaxy by galaxy, orbit by orbit. Vera Rubin spent her career proving that something unseen holds galaxies together. Now a telescope with her name looks outward to see just how many there are. Somewhere in that data, invisible mass still shapes every galaxy it touches. The observatory cannot see dark matter directly. No instrument can. But it can trace where galaxies bend and cluster and spin. In that pattern, the old evidence Rubin once found by hand appears again. Only now it appears across billions of galaxies instead of a few dozen. The sky above that Chilean mountain holds still tonight. The telescope keeps watching, patient and precise. The stars it captures tonight were already ancient before the mirror was built. Their light simply arrived at the right place, at the right time, to be seen. A decade is a long span for any instrument to hold its gaze on one part of the sky. But the reward is a record that no single lifetime of observing could have produced alone. Night by night, the picture grows more complete. Somewhere in the data yet to come, new questions about the universe are already waiting to be asked. Some of those questions have not been imagined yet. They are simply waiting in the dark for the right exposure on the right night to come into view. Two numbers describe the same thing. They refuse to agree. Both measure how fast the universe is expanding right now, not billions of years ago. Today, scientists call this number the Hubble constant. Its job is simple. Tell you how quickly space stretches as distance increases. One method looks backward, all the way to the early universe, to the faint afterglow left by the Big Bang. That afterglow carries a pattern of tiny ripples. They were frozen into light nearly 14 billion years ago. From that pattern, researchers calculate a predicted expansion rate. They use a cosmological model that has worked reliably for decades. The number that comes out sits close to 67 kilometers per second per megaparsec. The other method looks outward instead of backward. It uses stars close enough to measure directly. These are the standard candles introduced earlier in this story. Chain enough of these stars together, galaxy by galaxy, and a distance ladder forms. At the top of that ladder sit supernovas, explosions bright enough to see across the observable universe. Their light stretches as space expands. That stretch reveals a present-day expansion speed. This second method lands closer to 73 kilometers per second per megaparsec. Two independent methods. Two carefully built paths. Two numbers that should match. They do not. The early universe number comes in slower. The nearby universe number comes in faster. Consistently, the gap is not small enough to dismiss as noise. It has a name: the Hubble tension. For over a decade, researchers expected sharper instruments to make the gap close on its own. Better telescopes were supposed to help. So were cleaner data and larger samples of stars. Instead, each new measurement has sharpened both numbers. It has not pulled them any closer together. Sometimes the gap widens slightly instead of shrinking. This pattern is unusual in science. Most disagreements fade as data improves. Normally, errors get found. Assumptions get corrected. Numbers eventually converge on one answer. Here, convergence has not happened. Not despite years of dedicated effort. The teams running these measurements are careful. Every plausible source of error has been checked. Instrument calibration, interstellar dust, and statistical noise have all been tested repeatedly. Each team has spent years hunting for a mistake hidden somewhere in its own method. So far, no one has found an error large enough to close the gap completely. This leaves two possibilities. Both are strange to sit with for long. The first is simple to state. A measurement error still exists, somewhere in the chain. It might hide in the distances measured to nearby stars. Or it might hide in the ancient light left over from the early universe. A subtle flaw, still uncaught after years of scrutiny, would explain everything. The second possibility is heavier. Both measurements might already be correct. If that is true, the model connecting them is missing something important. The standard model of cosmology explains an enormous amount about the universe. It accounts for the structure of galaxies. It accounts for the behavior of light across billions of years. But it rests on assumptions about matter, energy, and the exact conditions of the early universe. If even one of those assumptions is slightly wrong, the predicted expansion rate would shift. The two numbers could split apart exactly as they have. Some researchers suspect something unusual happened in the first fraction of a second after the Big Bang. A brief event that nudged the universe's early growth in a way current models do not capture. Others suspect dark energy is not constant. They think its strength may have changed slightly over time. If dark energy varies, that alone could account for the mismatch between the two numbers. None of these ideas has been confirmed. Each remains an open hypothesis. Every proposal is tested against new data as it arrives. Every proposal still stands unresolved. Consider what the tension actually represents. Two teams, working independently, using completely different physical processes, are measuring the same quantity. Their results do not match. The gap sits well outside expected uncertainty. Statistically, a mismatch this consistent should not happen by chance. The early universe method relies on plasma physics from the universe's first few 100,000 years. The nearby method relies on the physics of pulsating stars and exploding supernovas. Both branches of physics are understood extremely well. Both methods have been refined for decades. And still, after all of that scrutiny, the two numbers disagree. Think about how long 14 billion years actually is. Almost the entire history of the universe sits between that ancient light and tonight. Across all of that time, the two methods were never trying to fool anyone. They were simply built from different evidence at different moments, using different tools. That they land on different answers is the puzzle itself. Not a mistake by either team, at least not one anyone has found yet. This gap sits at the edge of what is currently known about the cosmos. It is not a flaw scientists are ignoring. It is a puzzle they are actively chasing. New instruments have been built specifically to sharpen these two measurements further. More data has only deepened the disagreement instead of softening it. Whatever the final explanation turns out to be, it will not be small. If a hidden measurement error is eventually found, it will need to be substantial, large enough to account for over a decade of stubbornly resistant data. If the cosmological model itself needs revision instead, that revision will ripple outward. It would touch how the universe's age is calculated from first principles. It would touch how astronomers understand the earliest chapters of cosmic history. It would touch predictions about how the universe evolves in the distant future. Even the instruments themselves carry decades of careful engineering behind them. Mirrors polished to tolerances smaller than a wavelength of light. Detectors cooled to keep faint signals from drowning in noise. None of that precision has been enough to settle which number is right. Precision, it turns out, is not the same as agreement. For now, the disagreement simply stands. It is present in nearly every fresh dataset collected. Two measurements are pointing toward two slightly different realities. Both cannot be describing the same universe with perfect accuracy. Something, somewhere, is still missing from the picture. It may be a missing correction hidden in the instruments. Or it may be a missing piece of physics hidden in the model itself. Nobody yet knows which explanation is correct. 67 on one side, 73 on the other. Neither team has blinked. Neither number has moved toward the other in any meaningful way. The universe keeps expanding regardless of which answer eventually wins. Every galaxy drifts slightly farther from every other galaxy with each passing second. The exact rate of that drift remains, for now, a question with two answers. Neither number is willing to yield to the other. Both sit at the edge of what astronomers currently understand. The disagreement is small in raw terms, just a handful of kilometers per second per megaparsec. Yet across billions of light years, that small gap adds up to something impossible to ignore. It shapes how old the universe seems. It shapes how its most distant structures are understood. A single unresolved number, quietly reshaping an entire picture of the cosmos/texty 9/invoke. The James Webb Space Telescope was built to see farther than any instrument before it. It gathers ancient light. That light left its source long ago. It has been traveling ever since, crossing billions of years of empty space, before finally reaching a mirror built to catch it. When Webb opened its eye to the early universe, astronomers expected to find infancy. They expected small clumps of gas, faint sparks of new starlight. Instead, they found galaxies that already looked grown. These galaxies appeared massive, clearly structured. Some were already shaped into spirals with glowing, dense cores. They existed earlier in cosmic history than anyone had predicted, sitting in images of a universe that should have still been young and formless. The window of time available for them to form looked far too narrow. By the standard models, that window was not enough. Astronomers began calling these the impossible early galaxies. The name is not poetic exaggeration. It reflects a real tension inside the data. For decades, the story of galaxy formation followed a slow arc, one shaped by patience rather than speed. Gas clouds cool. Gravity pulls scattered matter together. Small structures merge into larger ones, one gradual collision at a time. This takes an enormous amount of time according to the standard model. Small pieces come first. Then, bigger pieces. Then, eventually, galaxies like our own. Webb's early images did not follow that gradual arc. They showed grown structures appearing too soon in the timeline. At first, some scientists suspected a measurement error. Telescopes can misjudge distances. Light can be misread. Age can be miscalculated in small but meaningful ways. But the data held steady under closer scrutiny, even as researchers checked and rechecked their instruments and their math. Team after team confirmed the same pattern. Independent surveys, calibrated separately, pointed in the same direction. Something in these early images was genuinely old and genuinely large. It should not have existed yet, by the standard timeline. Consider what building an ordinary galaxy requires. Stars must form in great numbers, then live out their long lives. Many of them die, scattering their remains into the surrounding gas, seeding the next generation with heavier material. Only then can heavier elements gather into new stars and new structures. This does not happen quickly. It unfolds slowly across long stretches of cosmic history that stretch far beyond a single human lifetime, or 100 lifetimes. Yet here were galaxies glowing with signs of maturity, present almost from the start. Astronomers began asking a quiet, unsettling question. What if the early universe built its structures faster than expected? Faster than gravity, moving at its usual pace, should have allowed? Several ideas emerged to explain the gap. One idea involves the efficiency of early star formation. Perhaps early galaxies converted their gas into stars with unusual speed. Not gradually, but in short, intense bursts. If true, the same material could build a galaxy far sooner than the old models allowed. Another idea looks at the invisible scaffolding underlying the cosmos. Long before galaxies form, unseen matter gathers into a web of filaments stretching across unimaginable distances. Ordinary matter later falls into that hidden structure. Some researchers wonder if this scaffolding formed earlier than assumed. If the web was ready sooner, galaxies could have grown into it sooner too. A third idea is more cautious. It points toward measurement itself. It suggests the masses of these galaxies may have been overestimated. Brightness can be deceiving. Certain young stars burn hot and blue, mimicking the light of an older, heavier galaxy from a great distance away. If some of that light comes from fewer stars, true mass could be lower. That would ease the tension without breaking the standard model entirely. No single explanation has been confirmed. The scientific community remains divided and appropriately cautious, but the underlying pattern is no longer in serious doubt. Too many independent observations, gathered by different teams using different methods, point toward the same broad conclusion. Early galaxies grew fast, faster than long-held timelines had suggested. This is the strange gift of a telescope like Webb. It does not simply show us more of the universe. Sometimes, it shows us less certainty than we had before. Every new image is also a photograph of the deep past. The farther Webb looks, the older the light it gathers becomes. Some of that light left its source before Earth had even formed, before the sun itself had come together out of drifting gas and dust. Webb is not only observing distant objects scattered across the sky. It is watching the universe as a much younger place, a place that still seems to be writing its own early rules. Cosmologists have not abandoned the standard framework because of this. It still explains most of what astronomers observe across the sky, from nearby star clusters to distant, ordinary galaxies. But this particular puzzle refuses to resolve itself. It sits there, embedded in the data, waiting to be understood. It is a reminder that timelines can bend under new evidence. Growth can happen faster than expected, under conditions not yet fully understood. Somewhere in the deep and ancient dark, Galaxies were already taking shape. Spinning disks were forming, along with dense, glowing centers. This happened long before slow. Gradual models said it should be possible. These galaxies were early and strikingly massive. Those two words, together, do not sit comfortably inside the old story. For now, the universe keeps that particular secret close. Its light keeps arriving, one photon at a time, each one a small message sent from a much younger cosmos. Each one carrying an ancient message. Let your breathing slow, with that thought settling over you. Somewhere, far beyond anything visible tonight, galaxies were forming ahead of schedule, quietly and without explanation. The universe was busy from the very start of its long history. It did this in silence, in complete darkness, long before there was anyone here to watch it happen. /text, /invoke. The oldest light in the universe still reaches us tonight. It has been traveling for billions of years, moving through the dark in every direction at once. Scientists call it the cosmic microwave background. Most people just call it the afterglow. It is the leftover light from the Big Bang itself, though not from the explosion. It comes from the moment right after. That was when the universe cooled enough for light to finally move freely. Before that moment, everything was fog. The early universe was a hot, dense plasma of particles, packed too close together for light to pass through. Every photon crashed into an electron almost instantly. Trapped, scattered, going nowhere at all. Then, not long after the beginning, something changed. The universe cooled below a certain threshold. Electrons and protons combined into neutral atoms for the first time. Space became transparent. Photons were suddenly free to travel. They shot outward in every direction, unobstructed at last. They have been traveling ever since, crossing the growing universe without stopping. That light is still out there tonight. It surrounds us now, in every direction you could possibly point. It has cooled and stretched with the expanding universe over billions of years. What began as a blinding white glow now arrives as faint microwaves. Just a few degrees above absolute zero. Cold, quiet, and everywhere at once. If you could see microwaves with your eyes, the whole sky would glow softly. It would be an even, gentle hum of ancient light wrapped around the entire sky. For decades, that is what scientists expected to find when they looked closely. A perfectly smooth glow, uniform in every direction, without a single blemish. But when instruments grew sensitive enough to measure it closely, they found something else. The glow was not perfectly smooth after all. It had tiny variations woven through it. Ripples in temperature, far too small to feel or see. Barely there at all. Easy to overlook. Almost too small to matter. At first glance. Except they mattered enormously to everything that came after. Those tiny variations were not noise. They were structure, quietly recorded in the oldest light there is. They were the fingerprints of a universe still taking shape. In the smooth plasma of the early universe, matter was not perfectly even. Some regions were slightly denser than others, packed a little more tightly. Only slightly denser, nothing dramatic. Just a whisper of difference between one patch of sky and the next. But gravity does not need much to start working. Denser regions pulled in more matter than their surroundings. Slowly, patiently, over hundreds of millions of years, the pull continued. Those small overdensities grew heavier with time. They pulled in gas from the space around them. They pulled in dark matter as well. Unseen but still governed by gravity. They became the seeds of everything that followed. Every galaxy you have ever heard of began this way. in this same quiet manner. It started as a faint variation in the afterglow of creation. A region only slightly more crowded than its surroundings, nothing more. Nothing dramatic marked it at the time. Just enough of a head start to matter later. Gravity did the rest, patiently, across billions of years. Over that time, those small seeds became galaxies. Galaxies gathered into clusters, drawn together by their combined gravity. Clusters gathered into vast, threading structures that stretch across the sky. The pattern you see in the ancient light is the blueprint for all of it. The universe left itself a map, written in temperature and shadow. That map was drawn before a single star ever existed. The instrument most responsible for reading that map in detail was a satellite named Planck. It spent years staring at the whole sky without pause. It measured those temperature differences with extraordinary precision, patch by patch. It mapped every ripple, every subtle variation across the entire sky. The result was a picture of the infant universe, an image of the universe as it was, incredibly young and still forming. A speckled pattern of warmer and cooler patches, faint but consistent. Each patch corresponded to a slightly different density of matter. Each patch was a seed, waiting to become something larger. From that pattern, something remarkable became possible. Scientists could work backward from the ripples to the universe that made them. They could calculate how much matter must have existed to create ripples of that size and shape. Not just the matter you can see with a telescope. All matter, visible and invisible alike. The ripples in the afterglow are sensitive to more than light and gas. They respond to gravity itself, in whatever form it takes. And gravity comes from everything with mass, seen or unseen. That includes matter that gives off no light at all. Dark matter does not shine. It does not interact with light in any way we can detect directly. But it has gravity, and gravity leaves marks. Those marks appear even in something as old as the afterglow of creation. By studying the exact size and spacing of the ripples, scientists could measure the makeup of the universe. They could work out how much of it is ordinary matter. That means the atoms that make up stars, planets, and everything you have ever touched. The answer turned out to be small. Ordinary matter is just a sliver of the total. Only a small fraction of everything that exists. The rest was harder to explain with light alone. A much larger fraction had to be dark matter. It is invisible, but gravitationally present in every measurement. It has been shaping the ripples since the very beginning. Beyond that, an even larger portion was something stranger still. It is an energy woven into space itself. It pushes the universe to expand faster as time goes on. The measurements from that ancient light were gathered independently by different teams and instruments. They matched other methods of measuring the universe almost perfectly. Different techniques, different instruments, all converging on the same numbers. Ordinary matter came out as a small fraction of the whole. Dark matter came out as a much larger fraction. Dark energy made up the majority of everything. 3 ingredients, confirmed by the faintest ripples in the sky. They were written into light older than any galaxy. It is a strange thing to consider on a quiet night. The light your eyes could never see, arriving from every direction at once, carries a census of the universe. It is a record of how much of everything there is, and a record of how little of it we can actually see. The pattern also tells a deeper story than that. It tells not just how much matter exists, but where it started. A slightly warmer patch, somewhere in the ancient sky, barely different from its surroundings. And yet enough. The universe did not begin as chaos with no direction. It began with faint suggestions, scattered quietly across the sky. Soft variations, barely different from their surroundings at first. Nothing more than that was needed. Given enough time, and gravity's patient pull, a whisper became a galaxy, and a ripple became a home. The afterglow still surrounds the Earth tonight, faint and unseen. It is cold, patient, ancient. It carries the same pattern it has carried for billions of years, a map drawn long before there was a sky to look up at, or eyes to look up with. Somewhere in that pattern is the seed that became everything familiar to you now. The stars, the galaxies, the quiet dark spaces between them. All of it was confirmed independently by light that has been traveling since before the first atom formed. The universe kept a record of its own beginning. It has been waiting patiently for billions of years to be read. Not every empty place in the universe is small. Some are vast beyond ordinary imagination, stretching across hundreds of millions of light years. Astronomers call them voids. They are regions where galaxies simply stop appearing, not because something destroyed them, but because very few ever formed there at all. One of these voids sits closer than you might expect. It surrounds our own galactic neighborhood, and astronomers call it the local void. It stretches for roughly 150 million light years. On one side of the Milky Way, matter thins out. Galaxies become sparse, then rare. Then, for a long stretch, there is almost nothing at all. The local void was not always obvious. For decades, astronomers mapped galaxies in every direction, expecting roughly even coverage. Instead, one direction kept coming back empty. At first, this seemed like a mapping error. Something telescopes were simply missing. Dust, perhaps, blocking the view. Or a gap in early survey coverage. But the more precisely astronomers measured, the more real the gap became. There was no dust to blame, and no missing survey. The space was simply not filled with galaxies. Survey after survey came back the same way. The count in that direction never rose. Eventually, the pattern could not be dismissed. A true void sat near our own galaxy. Our own galaxy sits near the edge of this void, not in its center, but close enough to feel its influence. Empty regions of space still exert a kind of pull. Or rather, their emptiness creates an imbalance. Matter around a void gets tugged outward, away from it, over time. Astronomers can detect this motion by watching how galaxies drift. Ours drifts too. Part of our galaxy's motion through space comes from repulsion, not attraction towards something, but a push away from where nothing is. The local void influences motion across tens of millions of light years. Matter has been flowing away from it for billions of years. That flow is slow by human measure. But over cosmic time, it adds up steadily. Galaxies on the near side drift a little farther with each passing era. The void widens slowly as its neighbors retreat outward. The local void is large, but it is not the largest void known. Farther away, much farther, there is another kind of emptiness, one that dwarfs the local void in scale. It lies in the direction of a constellation called Bootes. Astronomers named it the Bootes Void. It spans several hundred million light years. That number is difficult to hold in the mind. Light itself needs hundreds of millions of years just to cross it. Inside that volume, galaxies are almost entirely absent. Early surveys found only a handful, scattered across an enormous space. For a region so large, that number was shocking. If our galaxy sat at the center of the Bootes Void, the sky would look nearly blank. No visible neighboring galaxies for a long, long way. Just distant light, sparse and faint, scattered across the dark. Astronomers sometimes describe this scenario for scale. Not because it happened to us, but because it did happen. Somewhere, If any civilization formed inside the Boots void, their night sky would be almost featureless. No bright galactic neighbors overhead, no dense clusters filling their view. Only the dim, ancient light of very distant structures. They would have no easy way to know galaxies exist elsewhere in abundance. Their part of the universe would simply look empty to them. That thought unsettles some people. It means perspective can be an accident of location. What looks like the whole universe might be a local exception. The Boots void was discovered through painstaking survey work. Astronomers counted galaxies across wide areas of sky, region by region. Slowly, they built a map. Most regions showed a scattered, familiar density of galaxies. Then, one region showed almost nothing. At first, the count seemed impossibly low and hard to believe. Follow-up surveys confirmed it, again and again. The emptiness held. It was not a gap in observation. It was a gap in structure itself. The universe is not smooth, and it never was. Tiny differences in density, present from the very early universe, grew slowly over time. Regions slightly denser than average pulled in more matter. Regions slightly less dense lost what little they had. Over billions of years, that difference widened into something enormous. Dense regions became galaxy clusters, bright and crowded with light. Sparse regions became voids, dark and nearly empty of anything at all. The universe organized itself this way, gradually, through gravity alone. Voids like the local void and the Boots void are not failures of that process. They are simply part of it, as much as any cluster is. Every void has a shape. Every void has boundaries where its emptiness ends. At the edges, galaxies begin to reappear, sparse at first, then denser, forming the walls that outline the void's shape. These walls connect to other structures, stretching far beyond any single void. Filaments of galaxies stretch between voids like a loose, cosmic lattice. Voids sit inside the gaps of that lattice, quiet and mostly still. They are not scattered randomly across the sky. They fit into a pattern that spans the observable universe. Seen from far enough away, that pattern looks almost like a sponge. Dense filaments woven through, with vast empty chambers in between. We happen to live near the edge of one of those chambers. Two of those chambers, one near and one distant, show how wide the range can be. A void does not announce itself the way a galaxy does. It has no light to offer, nothing bright to draw the eye. Its presence is measured by absence, by counting what is missing. That kind of discovery takes patience. It takes careful, repeated observation across enormous distances of space and time. The reward is a strange kind of knowledge, knowing exactly where the universe chose not to build anything at all. Somewhere out there, hundreds of millions of light years wide, is a stretch of space almost untouched by galaxies. It has been that way for a very long time. It will likely stay that way for a very long time more. Closer to home, our own void keeps drifting outward too. Slower, smaller, but no less real. Density pulled matter one way, across billions of years. Its absence pulled matter another way, just as steadily. The result was structure on the largest scales we can measure. Bright filaments here. Silent gulfs there, stretching on in the dark. Our galaxy happens to sit near one of the quieter regions. Not at its heart, not at its edge, but somewhere in between. Astronomers keep refining these maps, survey after survey. New surveys look farther and count more carefully than before. The boundaries of the local void grow sharper with each pass. The Boots void keeps its shape too, vast and mostly empty. Neither has filled in over time. Neither is expected to fill in soon. The universe filled itself unevenly, without any plan, and in certain places, it barely filled itself at all. Ein/texti, 9/invoke. There is a rule that holds everywhere. It does not care where you stand. It does not care which direction you face. Look far enough, and the universe stops looking strange. It starts looking the same. This is a strange thing to say about a place full of emptiness and fire, full of galaxies clumped together, full of vast regions with nothing at all. Up close, everything seems random. A cluster here, a void there, a bright knot of stars, then nothing for a very long stretch. If you only looked at your own neighborhood, you might think the universe was chaotic. You might think it had no order. But step back far enough, and the clumps start to blur. The voids start to average out. What remains is something smoother than you expected. Cosmologists have a word for this. They call it homogeneity. It means that on the largest scales, matter is spread out evenly. Not perfectly evenly, but evenly enough that no region is truly special. There is a second word that goes with it. Isotropy. It means that no matter which way you look, the view is roughly the same. Look north. Look south. Look toward a distant corner of the sky you will never visit. The pattern of galaxies, on average, does not change. This does not happen at small scales. A single galaxy is not evenly spread. It has a bright center and a thinning edge. A small patch of sky is not isotropic either. Point a telescope one way, and you might catch a cluster. Point it another way, and you might catch nothing. The rule only appears once you zoom out far enough. Far enough that individual differences stop mattering. Scale is the whole story here. At the scale of a single galaxy, structure dominates. At the scale of a small cluster of galaxies, structure still dominates. Only once the sample grows large enough does the structure start to wash out. Picture a very large cube of space, vast on each side, far larger than any single cluster. Count the galaxies inside it. Now take another cube somewhere else entirely, just as vast across. Count again. The numbers come out close, not identical, but close. Try it a third time, in a completely different part of the sky. The number comes out close again. Do this again and again, in different places, in different directions. The averages keep converging. Push the cube even larger, and the convergence gets tighter still. This is what a statistically uniform universe looks like from the inside. It is not a universe without structure. It is a universe where structure repeats at a certain scale. Repeats until it stops mattering which particular repetition you happen to be standing in. Think of a forest. Stand next to one tree, and it looks nothing like the tree beside it. One is taller. One leans a certain way. One has more branches on its left side than its right, but step back far enough to see the whole forest. The individual trees blur together. What is left is a general sense of how dense the forest is, how tall it tends to be, how the canopy spreads. The forest as a whole has a character that no single tree can show you. The universe works the same way. Every galaxy is different. Every cluster has its own shape, its own history, its own particular string of collisions and mergers. But the forest of galaxies, taken as a whole, settles into a steady pattern. This pattern is not obvious. It took a long time to notice it. Early observers only had small patches of sky to study. Small patches showed clumps and gaps, with no clear order. It was only when surveys grew larger that the evenness began to emerge. Wider stretches of sky, deeper stretches of distance. The bigger the sample, the smoother the average became. A narrow sliver of sky can hide the pattern entirely. Spanning a wider fraction of the sky tends to reveal it instead. Depth matters as much as width. Looking only nearby captures a thin shell of the universe. Reaching far back in distance captures a much thicker shell. The thicker the shell, the more the pattern has a chance to show itself. Distance and direction work together this way. Neither one alone is enough to see the whole picture. Only both, combined, let the pattern come into focus. This evenness matters for a very practical reason. It is the reason cosmologists can study the universe at all. No one can visit every corner of space. No one can measure every galaxy, every gas cloud, every scattering of dust. There are far too many, spread across distances too vast to cross. A full census would take more time than anyone has. It would take more instruments than anyone could ever build. But if the universe is roughly the same everywhere, on large scales, this problem shrinks. A sample from one region can stand in for the whole. A patch of sky studied carefully can represent countless other patches never observed directly. Consider how this works in an ordinary kitchen. Taste one spoonful of a well-stirred soup, and you learn something about the whole pot. You do not need to drink it all. One spoonful is enough, as long as the pot has been properly stirred. If the soup is still separated into layers, that shortcut fails completely. One spoonful from the top would tell you nothing about the bottom. The universe on the largest scales behaves like the stirred pot, not the separated one. This assumption has a name of its own. It is often called the cosmological principle. It says that the universe, viewed on a large enough scale, has no special locations and no special directions. No preferred center. No favored edge. Every sufficiently large region looks statistically like every other. Take one corner of the observable universe. Take its exact opposite, on the far side of the sky. Neither one gets to be the exception. This does not mean every region looks identical in exact detail. It means the broad properties settle into the same pattern no matter where you sample. Density, the mix of matter, the way structures cluster together. Without this idea, modern cosmology could not function the way it does. The same physical laws could still apply everywhere, in principle. But there would be no way to check that from a single vantage point. There would be no way to generalize a measurement taken in one place to conclusions about the universe overall. The cosmological principle is what lets a limited set of observations describe something far larger than anything a single observer could ever see directly. It is a quiet kind of order. It hides behind everything that looks disordered up close. Every void you could point to, every dense cluster, every gap and knot, exists within a wider pattern that flattens out. Zoom in, and you find endless variation. Zoom out, and the variation dissolves into a single, steady average. This is one of the deepest properties of the universe. Not that it is empty, not that it is full, but that whichever it is that way consistently, in every direction once you look widely enough. It took generations of careful counting to trust this idea. Each new survey added its own patch to the total. Each patch, checked against the others, told the same quiet story. No single observation could have proven it alone. Together, they built something steadier than any one measurement could offer. That is the strange comfort in it. A law with no exceptions is easy to lean on. It does not shift when you move. It does not change its mind between one direction and the next. Wherever the next measurement comes from, it already knows roughly what to expect. That certainty is rare, in a universe built mostly from unrepeatable events. Most of what happens out there happens once, in one place, in one way. A star forms only where conditions allow it. A galaxy merges with its neighbor only when their paths happen to cross. None of that repeats exactly. anywhere else. But the average of all of it repeats everywhere. The single events stay strange. The pattern behind them stays constant. That is the rule this chapter is named for. A single quiet law, humming beneath all the noise. It waits in every survey that reaches wide enough to catch it. It waits the same way in every direction you might choose to look. There was a time when the ending seemed settled. Scientists spoke of it plainly, as a fact rather than a guess. The universe would expand, and it would keep expanding. Nothing in the models suggested it would stop. Galaxies would drift apart, slowly at first, then faster. Distances would grow too vast to cross. Light itself would struggle to arrive from one galaxy to the next. This was called heat death, a slow fading rather than a fire or an explosion, a cooling that never truly ends. Consider the universe as it is tonight. Stars burn quietly across the dark. Galaxies cluster together, held by gravity. Light moves between them, carrying energy across immense distances. Energy flows from hot places to cold ones. And that flow is what makes anything happen at all. Heat death describes the moment that flow stops for good. Every star eventually burns out. Every source of light goes dark, one by one. Matter spreads so thin it barely touches itself anymore. Particles drift alone across distances too large to imagine. No new stars form after that point. No new light appears anywhere in the sky. Temperature slowly evens out across all of space. Nothing is hotter than anything else. And nothing is colder either. Physicists call this state equilibrium. It sounds peaceful, but it is not warmth. It is the absence of difference. The absence of any imbalance at all. Without difference, nothing can move meaningfully. No engine runs without a hot side and a cold side. No process can drive itself forward without that imbalance. The universe would simply sit there, cold and dark and silent, for what would feel like forever. This fate follows from one simple assumption. The assumption is that dark energy stays constant over time. Dark energy is the force pushing space apart, quietly, everywhere. For decades, most models treated it as fixed. A steady pressure that never changed its strength. If that pressure never changes, the outcome is heat death. Expansion continues without pause. It never slows, and it never reverses. Galaxies outside our own cluster eventually vanish from view entirely. Their light can no longer catch up to us across the widening gap. The visible universe would slowly shrink. Not because objects disappear, but because the space between them grows too fast for light to cross. Stars stop being born as the raw material runs out. The last ones burn their fuel and go dim, one after another. Black holes remain the longest of all, and even they eventually evaporate. That evaporation happens slowly, over spans of time longer than anything that came before it. What is left afterward is emptiness, a stretched, dark quiet, with nothing left to disturb it. No sound travels through it. No structure remains to tell any story. For decades, this picture held firm in the scientific record. It was treated less as a guess and more as a settled certainty. Textbooks presented it with real confidence. Conferences repeated it, and papers assumed it as a starting point. Few researchers thought to question it directly. Then new data arrived and complicated the picture. Between 2024 and 2025, a survey called DESI released fresh measurements. It mapped the positions of millions of galaxies across the sky. It tracked how fast the universe has expanded at different points in its long history. The results were unexpected, even to the researchers involved. Dark energy did not look perfectly steady after all. Its strength appeared to shift across cosmic time, subtly but measurably. Not wildly and not dramatically, but enough to matter. Enough to raise a real and serious question. If dark energy changes over time, the old assumption breaks down. A force that weakens could slow the expansion of space. A force that weakens further could let gravity pull galaxies back together again. That would not lead to heat death at all. It would lead somewhere else entirely. A collapse instead of a fade. Space contracting instead of stretching outward forever. An ending with motion in it, rather than stillness. Or the strength of dark energy could increase instead, following a different path. If it grows stronger, expansion could accelerate without any limit. Space would tear apart at every scale, galaxies first, then stars, then atoms themselves. A different kind of ending. Fast instead of slow. Violent instead of quiet. Nobody knows yet which path is the real one. The new measurements are still early in their story. They hint at change without confirming its exact shape. Researchers describe the signal as intriguing, but not yet settled. More data will be needed before any conclusion can be fully trusted. Future observations will refine these early findings over time. Until then, three broad outcomes remain open at once. A slow fade into cold and dark. The old familiar story. A dramatic tearing apart of everything that exists, or a collapse back toward a single point, reversing the expansion entirely. Each one follows from how dark energy actually behaves. Each one is still on the table right now. This uncertainty feels strange in a field built on precision. For years, cosmologists spoke of the far future with quiet confidence. Now they speak with far more care than before. The universe's ending is not disproven by any of this. It is simply less certain than it once seemed. Consider what that shift really means. For most of human history, no one could measure the universe's fate at all. The question belonged to philosophy, not to science. Then, for a few decades, science offered a clear answer. A cold, slow, empty answer that felt final. Now that answer has loosened, though it has not disappeared completely. The universe may still end in heat death, exactly as once predicted. The data does not rule that outcome out. It simply no longer rules everything else out either. There is something almost calming in that open space. It means the story continues, still being studied, still being measured, still being understood, piece by piece, year after year. Right now, satellites and telescopes gather more light from distant galaxies. More positions are recorded every night. More distances are calculated and checked. Every galaxy mapped adds another data point to the larger picture. Somewhere, a computer quietly processes those points. It searches for patterns across the long span of cosmic history. It is patient work, slow and careful and exact. The kind of work that takes decades to bear any fruit. Teams compare each new survey against the ones before it. Small differences matter more than they once seemed to. A shift in one measurement can nudge an entire model. Nobody rushes to a final answer. The caution itself is part of the process. For now, the universe keeps expanding, just as it has for billions of years. Space keeps stretching between galaxies, a little more each day. Light keeps traveling across that stretching space, carrying old news forward. And somewhere in the data, an answer is slowly forming. Not yet complete, not yet certain, but forming all the same, one measurement at a time. The heat death of the universe was once considered the only ending. Now it is one possible ending among a few real candidates. Cold and quiet, as once believed. or violent and sudden, tearing space apart, or a slow return to a single point, gravity winning in the end. The universe has not decided, or perhaps it has, and we simply have not measured it yet. Either way, the sky above you tonight holds the same stars it always has. The same quiet light, traveling the same long distance to reach you. Whatever the universe becomes, it will take an immense stretch of time to get there. Longer than any star burning above you now. Longer than any measurement yet taken by anyone. For tonight, the sky stays exactly as it is. Dark and vast and steady. Still unfolding its answer, one photon at a time. R/texty. R/invoke.